Hello, everyone. Welcome to Module 2. And we have three very short discussions here for this module. In this module, we'll be looking at the atmosphere, specifically a lot of the gases that make up the atmosphere and sort of what their role is in this whole discussion of global warming and climate change. So like the first module, I have an outline for you and I have some images to sort of help us along with this. And again, as I mentioned on the first module, if anything is unclear, please don't hesitate in dropping me a line. I'd be happy to clarify anything for you, okay? So let's go ahead and jump in here. I'll bring up the outline first of all. And so we'll begin our discussion here. So one of the things to sort of start this whole thing out is if we look at the global average temperature of land and water, specifically the oceans, we're talking about maybe 57 degrees Fahrenheit, okay? That is neither cold or hot, all right? So it sort of seems to be more of a temperate temperature, meaning that it's a very mild, generally speaking. We know that these are just simply averages. So obviously there are pockets around the globe that are much higher, pockets around the globe that are much cooler. All right. So anyway, we're going to look at some of these gases here. Some of these gases are fixed gases and they don't play a role in global warming or climate change. It's more the variable type gases that we have that is our big issue. Okay. All right. So to start off with, of course, we want to talk a little bit about the greenhouse effect. All right, so many of you are probably familiar with the greenhouse. You see them on farms. You might have one in your own backyard if you're growing vegetables or something. So you have this little house, and typically it has maybe a very transparent plastic or something that is it's made out of. Well, what we want to kind of keep in mind here is that what we have is that when we go from the sun to that greenhouse, it passes through what is commonly referred to as a translucent medium. The atmosphere is a translucent medium. And what that means is that the energy that we receive from the sun is traveling through that atmosphere before it finally hits the Earth's surface or it enters into that greenhouse. You walk into the greenhouse and it can be very, very hot and humid. All right, that becomes what is called passive energy or passive solar energy. As it passes through that plastic, it becomes trapped in there. Now, the greenhouse effect, of course, is very much a natural process. So let me go to an image here that might help us out a little bit. Okay, hopefully. All right, let's see, there we go. Okay, so let's take a look at this. And so let me just kind of walk you through the schematic. So this is a natural process that we have. So the amount of energy that we receive over the course of the day is not equal to what is radiated or lost back at night, okay? So as this energy makes its way down through the atmosphere, we know that some of this energy is going to be reflected back up into the atmosphere. Clouds have a very high albedo. What that means, albedo is reflectivity. Snow has a high albedo. Water has a tendency to have a high albedo. That just simply means reflectivity. So some of this energy that is given off by the sun hits the top of a cloud and it radiates back up into the atmosphere. We also have particles within the atmosphere. It could be dust, it could be smoke, it could be sand. That will also create an albedo process as well. We also know that we have gases in the atmosphere that will sort of absorb some of this stuff. So when we look at it, so it's kind of what is reflected, okay, back up into the atmosphere. The rest of that energy, of course, is absorbed by the oceans or it's absorbed by the land, if you will. And so what happens here is that we sort of look at how that sort of balances things out. So what we want to know with this is that what is being radiated back up into the atmosphere and what is also being trapped, okay? And it can be trapped by these greenhouse gases. It could be trapped by ozone, whatever the case may be. In a perfect world, we would like to see it balanced out. So meaning what is actually brought in is equal to the amount that is lost at night. That, of course, is not taking place with this, okay? So what takes place here when it comes to things like heat, we have what is commonly referred to as what is called infrared. Infrared radiation is not something that you and I see. We can't see it, but it's something that is actually sensed. All right. And so in something like this, we know that the oceans and the land are retaining or holding that heat. Land does not hold heat the way water does, and we've already had this discussion. But nonetheless, we know that the surface does absorb some of it. Think about it again. If you walk outside in the middle of the summer, in the afternoon, and you walk out onto a dark surface, okay, like a parking lot. Well, you know that that parking lot is very, very hot. The surface is very hot, but it's going to cool off very quickly. All right, it has that low specific heat. But we do know that the oceans do absorb a lot of this heat. And heat is radiated. So what we have here is that we have not only that energy that is gained over the course of the day, but what is trapped or absorbed, all right, by the surface of the earth, whether that's land or water, okay? And it radiates this heat, and this is what is called infrared. Now, let me just show you an image here real quick that sort of illustrates this with sort of this idea of infrared. Some of you have probably seen, you know, there are thermal cameras, things like that. There is what is a science called remote sensing, where what it is that you don't physically touch the object, you just sense the heat that comes off of it, all right? And so this is sort of a thermal image here that we could take a look at somebody's hand here. It's, you know, infrared radiation is what we emit, what is emitted and what we feel, okay? It's sort of what we sense. So when we look at this, if you look at this image here, you see the center of the person's hand is much warmer than, say, the fingertips that you notice sort of in that green color versus that reddish orange. That is infrared radiation. Now, what is important about this is that what we actually see that is emitted or is that is absorbed, all right, but also emitted that we have. So if you look at this, we have ocean heating. I want you guys to notice, and this comes from NOAA, all right, the National Oceanic Atmospheric Administration. You'll notice if I go back here in 1960, so a good 60 years ago, we see that there's not much of a heat content within the ocean compared to land. So you'll notice here sort of this reddish color, or this burnt orange, if you will. All right, this is actually the heat content of land. And this is what I've been trying to explain to you guys, why the role of the oceans are so significant in this discussion. So you'll notice here that since the 1970s, all right, we have seen a phenomenal rise in ocean heating. So with this, that kind of makes sense if 71% of the Earth's surface are the oceans, and they're the big absorber of heat, okay, they're also going to radiate. And remember I said to you, there is that epidemiological layer, all right, about the first 600 feet of the ocean surface that is really sort of absorbing and holding that heat. But that heat is also channeled to different depths because of the circulation of the ocean, because of the movement of water. That surface, all right, the tippy top of the ocean will absorb that heat, and then it's sort of brought through down to lower, all right, levels of the ocean. All right, that sort of holds that heat. So I want you to sort of see this, how significant the oceans, the role they play. This is also why I say to you that when we do sort of annual forecasts or seasonal forecasts, one of the first things that's looked upon, of course, are the sea surface temperatures. How warm or how cool are the oceans actually with this? So the behavior of the oceans, as I've explained to you, become very significant with this. And they're the big absorber of a lot of that heat. Now, in a perfect world, what we would like to see, as I said to you, is sort of the balancing out with this. So this is what is commonly referred to as a heat budget. So think of it this way. If you have, most of us, if not all of us, have a financial budget. So let's just say, for argument's sake, that $1,000 goes into your savings account every month. Well, you have that $1,000 to spend. So if you obviously spend more than that $1,000, you're obviously in the red, you are running at a deficit. If you spend less than that $1,000, you're in the black and you have a surplus. Well, what we've seen, of course, over the last 50, 60, 70, 80 years is that we continue to see a surplus of heat in the atmosphere. These are places, of course, that typically don't receive that kind of heat. So we look at things like if we go up and we start talking about higher latitudes or higher elevations, where we sort of see the melting of glaciers. The melting of glaciers has become very, very significant to us. And there are two types, and we'll talk more about this in detail later on. But I want to at least start setting the stage for you. If I take a glass, and I put ice in it, and I fill it up with water, and I just leave that glass there, and I let that ice melt. Does it really change the level of water in that glass? The answer to that is no. So it's not so much the oceanic glaciers that we're concerned about, the icebergs and things like that. I mean, we're concerned about it, but not like we are in terms of land ice sheets or land glaciers. But what happens here is that as those ice cubes melt, of course, it really doesn't change the level, all right, of that water. But if you sort of use that same analogy, when the icebergs start to melt, the level of the water doesn't really fluctuate a whole lot. But it's the land glaciers, it's the land ice sheets that we're most concerned about. So if I have ice sheets or glaciers that melt, of course, that water is going to drain into the oceans. Does that raise the level of the oceans? Yes, it does, because I'm adding that water to that. So if we know that the oceans are taking the brunt of this surplus of heat, we know that with it being 71% of the Earth's surface, that has a monumental effect on ice sheets, on glaciers. If the land is also absorbing heat to a certain degree, all right, we know that that has a huge impact on land ice sheets or land glaciers. So this is the concern that we have with respect to this. The budget is not, you know, you have $1,000 at the beginning of the month, at the end of the month, you have zero where it balances itself out. We're just seeing a surplus of that heat, okay? So that budget is becoming more skewed towards heat instead of cool or at equilibrium, meaning that it zeroes out. Okay, so let's go ahead here and take a look at sort of the composition of the atmosphere if we could. All right, so I want to point out to you that when we look at this, there's a number of greenhouse gases out there. And of course, GHG is going to be greenhouse gases. When we look at this, let's look at just the basic composition of the atmosphere. The atmosphere is made up of what are called the primary or fixed gases, and there's really three of those. And then we have a whole slew of these variable gases, and these are the ones that we're most concerned about when it comes to global warming and climate change. Now, I cannot exceed 100%. Okay, so when we look at this, I want to point out to you that the three primary gases make up more than 99% of the atmosphere. In our first module, I said to you that, hey, the atmosphere is this very thin blanket of air that surrounds the Earth, and it protects you and me and other life forms from harmful UV rays. It also helps in terms of looking at sort of balancing out temperatures. So let's go ahead and take a look at these very, very quickly. The first of our primary or fixed gases that make up about 78% of the atmosphere is nitrogen. All right, so nitrogen is the most abundant gas that we have in the atmosphere. It is not considered to be a greenhouse gas. Okay, it doesn't play a role really in our discussion of global warming or climate change. 21% of the atmosphere is made up of oxygen. Okay, so oxygen, obviously a very good thing. Oxygen does not play a role in this discussion as well. So when we look at this, if I combine these two, this accounts for 99% of our atmosphere. I can't exceed 100%. So I'm only talking about 1% more that I could possibly have of one more primary gas and the whole slew of greenhouse gases out there. My last of the three of primary gases, less than 1%, is made up of argon, A-R-G-O-N. Now, if I take these three primary or fixed gases, meaning that their percentages really don't fluctuate, it constitutes over 99% of the entire atmosphere. So that means the rest of the atmosphere is made up of all these variable gases. And this is where we start to talk about greenhouse gases, or those gases that pose the biggest threat to our atmosphere, okay? The key thing here, guys, is that it constitutes less than 1% of the entire atmosphere, but yet it is what we're looking at when we talk about global warming and climate change, okay? So I'm gonna go through these kind of quickly. All right, just so that you understand, and I sort of left this up, and there are 6 primary or principal greenhouse gases. That doesn't mean that we don't have more, but I want to sort of hit the big 6, if you will, in our big discussion here with this. Number 1, of course, is carbon dioxide. Carbon dioxide is considered to be a greenhouse gas, and of course, you and I can't survive without carbon dioxide. We need carbon dioxide in order to have photosynthesis, in order for us to be able to produce oxygen. We're going to talk a little bit more detail about these guys in our next discussion. I'm just trying to break this up for you guys, okay? So CO2, we talk a lot about that. It is probably the most powerful greenhouse gas we have. It holds heat for a very long period of time. Some of these gases don't hold heat for very long, okay? But carbon dioxide has the ability to trap and hold gas or heat, and it has a tendency to hold on to it for quite some time, okay? All right, so it has the ability really to hold and store it longer than any of the other greenhouse gases out there. The second one is that we have methane. All right, so methane is a strong trapping gas as well, but it doesn't hold it for a very long period of time. When we look at this, there's natural occurring methane. Of course, there's man-made methane as well that we look at, and we'll talk again more a little bit in our next discussion. The third one is ozone. Now, I explained to you guys in our first module that we have good ozone or we have bad ozone, but nonetheless, what we're concerned about, of course, is the bad ozone. The bad ozone you see many times here, especially in the winter months in the Western United States. When you look out, if you get up in the morning and it's the winter and it's a nice sunny morning, but you look out over the Carson Valley or you look out over Reno or, you know, maybe even Las Vegas, depending upon where you're at, you'll see sort of this white haze that just kind of goes right across the valley. That is typically ozone. That is a photochemical reaction, all right? That's the sunlight interacting with carbon dioxide or whatever, and it's converted into a greenhouse gas. This is the bad ozone, all right? So we'll talk more about that later on. The next one is nitrous oxide. Nitrous oxide, a lot of this that we get from, a lot of it we get from things like agriculture and mining. Okay, so there are some human aspects with this that we need to sort of look at. The next one, number 5, is what is called chlorofluorocarbons. I know that's a mouthful, okay? Most people just refer to these as CFCs. A lot of this comes from cooling agents, things like Freon, things you see in your car air conditioner, Freon you have in refrigerators. You get this also from aerosol cans, spray paint, things of that nature. All right, and those have an impact on the good ozone that you'll see here in a bit. The last one, and this is the most abundant one we have, and most people don't really sort of think about this as a greenhouse gas, but it is, and that's water vapor. So as you all know that, of course, water can be a solid, meaning ice, okay, liquid, obviously water that comes out of your faucet, or a gas. You know this mostly as humidity. Now, here in Nevada, we don't have a lot of humidity. We have very low humidity. But if any of you have ever spent any time in the Midwest or the Eastern United States, especially say the Southeast United States, it is oppressively hot and humid. If you've ever traveled to, other parts of the globe, places like Southeast Asia, it is beyond oppressive, okay? But that water vapor is considered to be a greenhouse gas, and it's the most abundant of all greenhouse gases that we have. The one thing, it has a very, very short life cycle, okay? We'll talk about that here in a little bit. Okay, so I want to keep this very, very brief. I promise you it would be. All right, we know that when we look at the greenhouse effect, we are running at a surplus of heat. The heat budget or the energy budget does not zero out, okay? Meaning we don't lose what we gain over the course of the day. Unfortunately, some of this heat is being trapped. So we're running at a surplus in this day and age. The energy that is emitted or radiated off the Earth's surface, whether that's land or whether that's ocean, is commonly referred to as infrared radiation, okay? It's something that we don't see, but we sense, all right? And of course, the key thing with this that I want to point out to all of you as you're reading, working on your assignments, is that the atmosphere is very, very delicate. You have three principal or fixed gases that constitute over 99%. It's the 6+ other greenhouse gases that we have out there that is causing all of this discussion that is taking place with global warming and climate change. So it takes very, 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 very little, guys, to manipulate the atmosphere. That's how delicate it actually is, okay? All right, so I will check back with you here in a bit. Okay, and so when you go into the next discussion, I'm going to talk mostly about some of these greenhouse gases. Okay, all right, I'll talk to you soon. Bye.